In this video, we're going to be looking at the various lifting mechanisms that can be potentially responsible for the formation of convective weather. The first type is forcing along a density discontinuity. By that we mean that there is one air mass that undercuts another and forces it to rise. For example, a cold front. In the case of a cold front, cold air undercuts warmer, less dense air, and oftentimes this warmer air contains more moisture, and so the virtual temperature is larger. So there's a contribution to the density difference, not only in terms of temperature but also in terms of moisture. This also occurs for warm fronts and things like outflow boundaries from thunderstorms, which we'll see in a movie loop a little bit later on, and things like dry lines, which are associated with troughs of low pressure. For example, in central New South Wales and Queensland and into northern Victoria during the summer, troughs form. They're an axis of minimum surface pressure, but they also represent a density discontinuity with warm, moist air on one side and hot, dry air on the other. So again, the difference in density isn't simply due to temperature differences, but also due to moisture. Another forcing mechanism is waves. Whenever you have a significant component of wind perpendicular to a mountain range, under stable conditions, waves can be set up, and it's shown in the illustration at the bottom, where you have alternating peaks of ascending air, which can be lifted to a level of condensation, and then descending parts where the air is unsaturated, and so you get regular saucer-shaped type clouds, and possibly at multiple levels, as you can see from the figure. So this is altocumulus lenticularis because it's lensed shape, and you can see on the picture on the right there's two levels of cloud there, the flying saucer-shaped cloud, and on the left from the NOAA library, streets of cloud separated by regular clear bands. This is not uncommon in wintertime, in particular in New South Wales in a strong westerly, or in Victoria in either a westerly or a northerly. A third mechanism is surface convergence. Low-level convergence from opposing airstreams or wind shear causes the air to rise. So things like sea breezes and lake breezes are an example of that, and also troughs of low pressure again. So we've talked about fronts, troughs. Topography also plays a role. Flow over topography means that the air is lifted. Sea breezes, where convergence occurs, dry lines, and outflow boundaries from thunderstorms. We're going to look at a rapid scan image now, so it's 1 minute imagery, and you'll see all sorts of phenomena happening. You should see convection being lifted on the sea breeze front, where the prevailing wind over the continent collides with the onshore flow of the sea breeze, and you'll see a lot of outflow from thunderstorms, the cold air out of the bottom of the storm as it collapses, and you'll see fresh convection initiated on those. So just sit and watch this clip. You can see thunderstorm convection really kicking off, and then you'll see the formation of an outflow boundary, which will run ahead of the old storm and kick off new convection. Again, there's another one pushing outwards. So these are the various lifting mechanisms that we see generating surface-based convection.